We're going to use these relationships extensively today. Here's our voltage V1, our primary coil, arbitrary direction for our current I1, it does not matter. Here is our arbitrary direction for our current I2, it also does not matter. Here's our secondary voltage V2. And what we found was the ratio of V2 to V1 was equal to our turns ratio. The ratio of our secondary current to our primary current was 1 over A, or N1 divided by N2. And if our dots are on opposite sides, these relationships are exactly the same, except that there will be a negative sign. All right, so the first thing that we're going to talk about today is so this is one application of a transformer that will probably make a lot more sense to you guys after you have had your microelectronics class next quarter, where we go through but some of you may have dealt with things like this before if you play guitar amplifiers and things like that. So an output resistances, whereas a speaker typically has a very, very small input resistance. And so in order to match the very large output resistance of the amplifier to the very small resistance of your speaker, you might use a transformer. Okay? So let's consider the case where we have, let's call this impedance matching. With some phasor voltage Vs. Let's call this voltage V1, this current I1 like so. Here's our turns ratio N1, secondary coil, N2 like so. This is going to be V2. Sorry, this should be I2. And then over on this side, we have our load impedance ZL. So what we are going by our voltage source looks like. We're going to be reflecting the impedance over to the prime using these relationships. Okay, so it should be fairly straight. This voltage V2 divided by this current I2, because that's all impedance is the ratio of phasor voltage express that current I1 in terms of the current I2 using the relationships that we detailed here. So what should V1 be in terms of V2? So I'm going to replace V1 with V2 over A. What will my current I1 look like? So I1 will be I times A, absolutely. The impedance seen at our primary, I'm going to call this ZL single prime, is simply going to be the ratio of that voltage, V2 divided by A, divided by I2 times A. Well, this is the same thing as V2 divided by I2 times a factor of 1 over A squared. V2 divided by I2 is simply the load impedance connected to our secondary, so ZL divided by a factor of A squared. So this is what the impedance from the secondary reflected to the primary looks like, okay? So if A is a very large number, so greater than 1, meaning that we have a step-up transformer, then the impedance at the secondary that's reflected to the primary is quite small. If, on the other case, we have a step-down transformer, so N1 is greater than N2, when we reflect the impedance, it looks very large, right? So now, let's work the exact same thing, but instead of reflecting the impedance from the secondary to the primary, let's see what happens when we want to reflect it the other direction. So if we have the following network, where now our load is connected to our primary side, so here's V1. Dot N1, N2. Just for the sake of argument, I'll make I2 with that direction. Here is V2. Here is I2. Now we're going to be reflecting our impedance connected to the primary across to the secondary. So how can I express this voltage V2 in terms of V1? Yes. Thank you. This one should be 1. Primary current. They should be in the same places. N1 is the number of turns in the primary. So the primary has a voltage of V1, the current of I1. N2 is the number of turns in the secondary. So the secondary has a voltage drop of V2 and a current of I2. So all the 1 and 2 just means it's primary and secondary, where I'm arbitrarily putting the primary on the left-hand side of the page and the secondary on the right-hand side of the page. Right. Because I'm saying that this source is supplying current and this load is absorbing current. It literally wouldn't matter. All right, so how can I express this voltage V2 in terms of V1? Let's scroll up to our relationship. So V2 is just A times V1, right? How do I express I2 in terms of I1? Well, it looks to me like I2 is just going to be I1 over A. So the impedance of the primary reflected to the secondary, I'm going to call that ZL double prime. It's literally just the input impedance we see looking from the opposite direction, is going to be A times V1 divided by I1 over A, which is going to look like A squared times V1 over I1, or A squared times ZL. So effectively, to move an impedance from the secondary to the primary, we divide by A squared. To move an impedance from the primary to the secondary, we multiply by A squared. So there's our impedance magic. Any questions on this? Hopefully fairly straightforward. All right. So we're going to take this concept and we're going to go a little bit further. So in each of these examples, we had a singly excited network, meaning that only the primary was excited or only the secondary was excited. Now let's look at what happens if we excite both sides. Yes. Sure. Literally not. So they are completely interchangeable. So we're just saying one side is the primary that has N1 turns. One side is the secondary because it has N2 turns. That's it. There's nothing stopping us from exciting one side versus the other. It's just whichever one we call the primary has N1, whichever one we call the secondary has N2. Everything is based off that. So like I said, if N1 is greater than N2, we have a step down. If N1 is less than N2, we have a step up. From there, yeah, completely and utterly arbitrary. All right, so now we're going to look at Thevenin equivalent circuits. All right, so like I said, we are going to have a doubly excited circuit. So we're going to have some source voltage VS1 over here. Let's put some primary impedance Z1 here. And then we're going to connect our ideal transformer. This is going to be our voltage V1. This is going to be our current I1. There's my dot. N1 turns, N2 turns. Here is going to be my current I2. The direction of these currents is completely and utterly arbitrary. I just want to state that here. This is going to be the drop across my secondary. Here's Z2. Here's my voltage VS2. And I'm going to label these terminals so that we have some idea of what the heck it is we're talking about when we're doing this. All right. So do we want to find the Thevenin equivalent circuit with respect to terminals A and B first, or with respect to terminals C and B? So effectively, do we want to see what the primary sees or what the secondary excitation sees? Primary first, okay. So we are going to try to find the Thevenin equivalent circuit as seen between terminals A and B. So we're going to start with a voltage and then we're going to work on them. All right. So I'm going to disconnect my circuit from terminals A and B. So here's voltage V1. Here is N1. Here's N2. V2. And here is VS2. Let me go ahead and define my currents here really quickly. So here's I1, I2. Here's where V2 should be. All right. So first question, hopefully an easy question. What is the current I1 in this one? 0. Why? Because it's the current flowing through an open circuit. Okay. So if I1 is equal to 0, what does I2 have to be? Also 0, because they're related by the turns ratio, right? So if I1 is 0, I2 should be, I think, 1 over A times I1, still going to be 0. If I2 is 0, what's the voltage drop across this impedance Z2? 0. So what's the relationship between V2 and VS2? They're the exact same thing, right? So V2 must be equal to VS2. Well, V1, which is going to be our Thevenin voltage seen between terminals A and B, because it's a short circuit voltage, is then going to be what? Go back to the relationships for the turns ratios and all that kind of stuff that we wrote at the very beginning of class. Is it going to be A times VS2, or is it going to be 1 over A times VS2? Which one? 1 over A. Okay. So our Thevenin voltage is going to be VS2 divided by A. Okay. I agree with that wholeheartedly. If we were going to find the Thevenin impedance seen between terminals A and B, right, we would turn off this voltage source. So we would be just reflecting this impedance Z2 from the secondary over to the primary side. So what would that be? We did it like 5 minutes ago. Z2 over A squared. Absolutely. So I'm not going to derive that because we literally just did it a moment ago. So our Thevenin equivalent circuit would look something like this. So here's VS1. Here's Z1. This is terminal A, terminal B, plus, minus, here's V1. Then we would have an impedance here that is Z2 divided by A squared. And then we would have a source voltage here that is VS2 divided by A. So we want to go in the opposite direction. What do you guys think is going to happen? Yep. So let's not even bother deriving this. You're 100% right. Okay. So we would have VS1, sorry, times A in series with an impedance Z1 times A squared. This would be terminal C. This would be terminal D. And then everything that was connected to the secondary is going to be left alone. So those are our 7 equivalent circuits referred to the primary and the secondary side. North, how may I help you? It isn't determining, we just decide. We say this one is the primary and the other one is the secondary. It depends on which one you're calling the primary and which one you're calling the secondary. You have a load on one side and you call it the primary side and you want to see how it looks to the other side, then you would multiply by A squared. Transversely, if you had stuff connected to the secondary side and you're just arbitrarily calling it the secondary side, and you want to see what it would look like if you referred it to the primary side, you would divide by A, the voltage, and divide by A squared. So it's all about just which one you call it, right? So every transformer, and this is where things get weird, is both a step up and a step down transformer, depending on which side you connect things to, right? Because as long as N1 and N2 aren't equal, and we also have transformers where they have the same on both sides, those are called isolation transformers, because you're just trying to electrically isolate one side of the circuit from another circuit without changing anything else. It's entirely up to you, right? So it does not matter which one you call the primary and which one you call the secondary, if it happens to have a larger number of turns on the other side or what. It's just pick one as the primary, the other side is the secondary, and then run with it. Because this factor of A multiplying by A squared might make things larger or might make things smaller, depending on whether or not the turns ratio is larger than 1 or less than 1. So it's all going to come out in the wash. Yes, ma'am. Kind of, yes. But so these equivalent circuits are specifically to show you what happens if we had a doubly excited, meaning we have a voltage source on both sides. The equivalent circuit, if we don't have a voltage source on both sides, is the exact same thing as the impedance matching or impedance appliance. Right. So we're saying I want to know what my voltage, when we do the impedance matching, we're saying I want to know what my voltage source on this particular side of the transformer is. So one interesting thing, and you'll learn more about this when you get into your, or if you choose to take your electric theory class and all that stuff. So, the model for the practical transformer is a little bit more rigorous than what we did in this class. Because we have to account for not only the losses in the windings of the primary side and the secondary side, which we touched on briefly, we also have to deal with losses, power losses due to magnetizing and demagnetizing our core over and over again. And then not only do we have to deal with the inductance of the windings, but we also have to do with the residual magnetization of the core, which is modeled as another inductance. So the real or the most accurate model for a practical transformer actually includes an ideal transformer. And so you'll use this concept of reflecting impedances back and forth to figure out what's seen on the secondary side versus what's seen on the primary side, depending on where you're connecting things like the load your sources and all that good stuff. So this is just kind of getting your toes wet, as it were, into a much more rigorous analysis of transformers in classes that are specifically meant to deal with this is how a transformer works. All right, so before we move along to our next topic regarding transformers, anybody have any questions about this? All right, so the next thing we're going to talk about is the ideal AutoTransform. So AutoTransformers are called AutoTransformers because they technically only contain a single coil, but still fulfill the role of a transformer. And this happens because that coil is tapped, which means a wire is placed, electrically connected at some point inside the coil, giving us access to not the full number of turns of the coil. So draw a picture here. So this is going to be a step down. And it might look something like this. So here is our source voltage. And this is the terminals of our AutoTransformer, over which we are going to have a voltage V1. We would have one long coil like so, and then a tap off of this coil, where our secondary is defined. So, and then we would connect this to some load. I'm going to define my primary current I1 in this direction and my secondary current I2 in this direction. And because realistically we only have one coil, there's really not a reason to have dots or anything like that, because if our current is flowing down, all of our flux is going to be passing through the coil in one direction. To make things easier for us to analyze, we are going to treat this thing as if it were a pair of coupled coils, right? And sorry, let me put something here where the total number of coils for this thing is n. So how we are going to approach the AutoTransformer is as follows. Effectively going to be practically the same diagram, except that we are going to split our coils. So this is our first coil. I'm going to put the dot here, and it will have N1 turns. This is going to be our second coil. I'm going to put the dot here. This will be N2 turns. And then here's our load impedance ZL. This is our secondary voltage V2. Our primary current still in the exact same place. And our secondary current is still in the exact same place. So before we analyze this thing, let me ask you guys, actually, let me do one other thing really quickly. I'm going to move N1 and N2 to the opposite side so that I can put the lines telling us that we're dealing with an ideal transformer. Effectively, these coils are still wound around the same core. Sorry about that. So, one thing that I want to point out here is that the current I2 isn't the current that's flowing through our secondary coil. What's the current flowing through our secondary? I1 minus I2. Absolutely right. So let's make a note of that really quickly. So in order to figure out how this thing works, let's first define our voltage DC, which is just going to be the drop over this bottom half of our coil, right? So I think it should be J omega times L2, whatever the inductance of that bottom half is, times the current I1 minus I2, plus J omega M. What's the current flowing through our first coil? Just I1. Right? So recall that L2 can be expressed as A squared times L1 to the turns ratio. So that's going to give us J omega A squared L1 times I1 minus I2 plus J omega M can be written as just A times L1 times I1. And so if I factor out J omega A L1, what I'm left with is, let me do this in square brackets, I1 plus A times I1 minus I2. Are we okay with this? Anybody have any questions, comments, or concerns? Yes, Daniel. Wonderful question. Okay. So Daniel just asked, it has nothing to do with this here in particular, but why you might use an auto transformer as opposed to a conventional transformer. So auto transformers are typically cheaper and they are typically smaller because they only contain a single coil that is kept. That being said, they do not provide electrical isolation between the primary and the secondary. So auto transformers are used a lot in power applications where you're stepping down the voltage from a really, so like in a substation, where you're stepping down the voltage from really, really high levels to a medium voltage type thing, where you don't necessarily need electrical isolation, but you're trying to drop the voltage by a significant amount. Whereas a conventional transformer, where we have two electrically isolated coils, so that's what like a pole pig transformer like you might see out here is made of, where you need that isolation between the two things. Yes. So a phone charger is an entirely different thing. So that's a rectifying circuit because your phone has a battery in it. And so to charge a battery, you need to apply a DC voltage and current. So you'll learn all about rectifiers in the first week and a half to 2 weeks of Electronics 1 with me next quarter. Now, that being said, well, so let me rephrase that. So that's a conventional phone charger, okay? And what I mean by that is that's one of those little blocks that you plug into a wall, and then there's a cable coming off of it that you plug into your phone. So that is what's called a rectifier circuit. Okay. That being said, if you have a wireless charging pad, that would be an example of a conventional transformer, in as much as the battery pack has an NFC antenna, near field communication antenna, resonates at a very specific frequency. And the charger itself also has a matched NFC antenna that resonates at the exact same frequency. That's also one of the reasons why the range on those suck, because the frequency is, I think, around 13. I don't remember if it's gigahertz or megahertz. It's been a long time since I tried them intentionally for the course. But effectively, the range on those is very, very small, which is why if your phone is even slightly ajar, it won't charge correctly. So that's, I hesitate to even call it a transformer, even though it's effectively doing exactly that. Like you have one coil that is electrically isolated from another coil. One is connected to 9 to 12 volts DC, depending on what the little cable has. And then the other one is connected to 3.3 to 5 volts DC, depending on what kind of battery your phone has. And you're just transferring power from one to the other. So it's behaving like a transformer, but it literally is two mutually coupled coils that only work because they're in close proximity to each other. So did I talk enough about phone chargers to satisfy them? Okay. So circling back around, are we okay with this expression for our secondary? Yes, James. Okay, so let me do this over here. And so A times L1 is going to be the square root of N2 divided by N1 over, or excuse me, times, no, I'm sorry. These shouldn't be N's, they should be L's. L2 over L1 times L1. So that's going to look like the square root of L1 squared times L2 divided by the square root of L1, which is, that cancels that, literally the definition of F. And then just for the sake of argument for the other thing, so A squared times L1 is L2 over L1 times L1 is just L2. And we derived those last Friday, but not a big deal if we didn't. Okay, so no problem. Any other questions about the relationship for the secondary voltage? Yes, Nathan. So I definitely want them on the same side, as it were, because I know that this is representing a single coil, so that any current flowing is going to cause the flux to flow through the same thing. Technically speaking, we could set things up where our tap effectively loops around, and we would have, like, I don't remember what we got, subtractive kind of interference type things, but that's generally speaking not a great idea, at least not for this particular application. So I chose to have the dot on top here and the dot on top here, because I know that I1 is going to flow through here, and then a portion of I1 is going to flow into the dotted terminal here as well, so that all of the math works out. Any other questions? All right, so now let's figure out what V1 is. So just to be clear here, V1 is the voltage defined from this point in the circuit to this point in the circuit. So it is going to include the voltage drop over this first coil, both the mutual term and the self-term, but it's also going to include the voltage drop over the second term, which we've already defined to be just V2. Right? So for the coil 1 portion of this, we're going to have J omega L1 times I1 plus J omega M times I1 minus I2, and then we're just going to add to that V2. Anybody have a problem with how I came up with this expression? Hopefully it should be fairly old hat. Okay, so I'm going to substitute in A times L1 for this M. So I'm just going to go ahead and throw in this whole expression here for V2. And so that's going to look like J omega L1 I1 plus J omega A L1 I1 minus I2 plus J omega A L1 I1 plus A I1 minus I2. And I'm going to lump some things together here. So I've got a common factor of J omega L. So J omega L1, excuse me, times I1 plus A I1 minus I2 plus J omega A L1 I1 plus A I1 minus I2. So that's going to look like J omega L1 times 1 plus A I1 plus A I1 minus I2. Anybody have a problem with that? So what should the ratio of our secondary voltage to our primary voltage give us? A? I disagree. Disagree with that as well. Opposite. A over 1 plus A, right? So there's a common factor of J omega L1 times this current. So I have an A left in the numerator and then a 1 plus A in the denominator. So it's going to look like A over 1 plus A, or N2 divided by N1 over 1 plus N2 divided by N1, which is just N2 divided by N1 plus N2. Why is this interesting? I know that's an odd question. Yeah, so N2 is the number of terms on the secondary side of this thing. N1 plus N2 is the total number of turns on the primary side of this thing. So it's still just the number of turns on the secondary divided by the total number of turns on the primary. It behaves exactly the same as a simple ideal transform, as we would expect. So what should our current relationship look like? So I2 over I1. So the total complex power supplied or absorbed by the primary has to be equal to the total complex power supplied or absorbed by the secondary. So it's just going to be effectively the inverse of this relationship. N1 plus N2 over N2. So those are our relationships for a step down AutoTransformer. A step up AutoTransformer is the exact same circuit, except that we put our voltage source on this side and our load on this, right? So let me draw it out really quickly. I don't know why File Explorer opened. And if we were going to derive things, which we're not going to do, we could look at this as if it were a pair of coupled coils again. Plus minus V2, I2, I1. What's the total current flowing through the coil to I1 minus I2? So, like I said, we're not going to derive things here, but if you wanted to, or if I decide to be a jerk and go through it, notice here that the voltage drop on the primary side is defined to be the voltage drop over the coil that has M2 turns, right? Seems wonky, but the math will work out finding all that. The voltage drop of V2 is the total voltage drop over this coil with N1 turns plus this coil with N2 turns. So how do you think this thing is going to behave? We're doing no analysis whatsoever, just what we learned from dealing with the step-down AutoTransformer. What do you think the ratio of V2 to V1 should be? So total number of turns on the secondary side, N1 plus N2. Divided by the turns on the primary side, which is just N2. Or I guess a slightly better way to put that would be the total number of turns seen by the secondary voltage divided by the total number of turns seen by the primary voltage. Okay. What should the ratio of current be? The inverse of the ratio of the voltages. So those are our auto transformers. Once again, they are used anytime we want to be able to handle a large amount of complex power. Effectively, you would use an auto transformer. All right, so any questions about step up and step? Yes, ma'am. Because the complex power on the primary side has to equal the complex power on the secondary side. So our primary side here, let me just, this will take 20 seconds to dry, right? So the complex power, excuse me, being supplied by the source is going to be V1 times I1 conjugate. This has to be equal to the complex power that's being absorbed by the load, which is going to be V2 times I2 conjugate. So we can rearrange this thing and we could find that the ratio of I2 to I1 conjugate and conjugate here is going to be equal to V1 over V2. So that means that we just take the reciprocal of our voltage. This is technically only true for ideal transformers, where we're not taking into account any losses that occur internal to the transformer. James, what's up? So, typically speaking, well, I guess it depends on what you mean by efficiency. That's another bag of cats as well. The friction, and well, there's not going to be friction because this isn't a motor. So I guess it would just be windage losses or whatever. Would probably be similar because it's just a lot of turns versus splitting it up among two coils. It's just one coil with a whole bunch of turns versus two coils with a smaller amount of turns. So I think they would largely be comparable. I don't know that one's going to be more efficient than the other. Right, but even in an electrically isolated one, all of the flux generated by one coil, effectively all of it should be passing through the second coil as well, because you're going to use a ferromagnetic core to effectively guarantee that that's going to happen. If you weren't winding your coils around a ferromagnetic core, then absolutely the auto transformer would have a better, it would have significantly less flux leakage because it's only a single coil. But from an ideal standpoint, where we're explicitly saying we're wrapping these coils around something that makes sure that the flux leakage is effectively zero, there should behave effectively the same. Yes, Andrew. So that's a really good question. Not really. And so why I say that specifically is because it's the flux being generated by one coil that's passing through the second coil that's causing things to happen. Whereas in an auto transformer, all of the flux is being caused by the same coil. So there's not flux being coupled from two separate coils. Now that being said, and tapping of a conventional transformer absolutely happens. And that's what happens in our homes. So this is just a quick aside thing. But you might see something where we have a conventional transformer. So let's call this our primary side. I don't know what the number of turns is. We'll figure that out in a moment if we choose to do so. And this voltage on the primary side would have a magnitude of, say, 13.5 kilovolts RMS. And then on the secondary side, we'd have something like this. Let me give myself more room, actually. Where the potential difference between here and here is going to look like 240 volts RMS, but we would tap the center such that we would get plus 120 volts RMS like this, and plus 120 volts RMS 180 degrees out of phase like that. That is literally how your home is set up. 240 volts is what's required by your larger appliances like your oven, dryer, and things like that. 120 volts is what's required by your smaller appliances. So you actually have two different 120 volt lines in your home that are exactly 180 degrees out of phase. And then when you add those guys together, it looks like 240 volts. So that is legitimately an example of what you were asking about, and it's in every single one of our homes. Well, this is standard for a single family home. Let me state it that way. Because if you live in a larger apartment complex, instead of having access to 240, you probably have a delta connected 208. And that's why most appliances here in the States can run off of either 240 or 208 volts RMS. And then, so that would be your line to line voltage, and then your line to neutral voltage would be the 120 volts required by your smaller appliances. So speaking of power distribution, three-phase transformers. Deriving nothing here, just drawing terrible pictures and telling you what the relationships are. Okay. So, first, bear with me. These are a pain in the ass to draw. I need to make that sound. All right, now let's make sure I don't cross wires that don't need to be crossed. Dot, 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 dot. This guy is going to jump over here. All right, And then I'm going to need, so let's call this A on the primary, B on the primary, and C on the primary. Let's call this A on the secondary, B on the, nope, C on the secondary. And down here, B on the secondary. This will be our line-to-line voltage, so VL on the primary. And this will be our line-to-line voltage, VL on the secondary. And the relationship between the primary and the secondary is just A. The current relationship is 1 over A. And the total complex power on the primary side is equal to, the total complex power on the secondary side. So this is the Y to Y pair. Let me know when I can scroll down and start working on the delta. Fantastic question. Currents, which I forgot to draw here. So we're just dealing with line currents. Like so. Thank you for that. So the L indicates that these are line-to-line voltages because we're measuring them between the transmission line currents. And the P is to the primary side, the F is to the secondary. May I start drawing the message? So our delta delta is going to be slightly more of a pain in the ass to draw. Dot, dot. All right, so this guy jumps over here. This guy jumps over here. Let's see, dot, 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 dot. So A on the primary, B on the primary, C on the primary, A on the secondary, Hold on, now I'm confusing myself. So let's see. C on the secondary, B on the secondary, VL primary, VL secondary, IL primary, IL secondary. All of the relationships are the same. Let me know when I can draw the last one. Yep. So this is obviously a delta delta, and I hear murmuring from the front row that, oh God, yes, there can be a delta Y and vice versa. That one, the delta to Y transformer is actually the easiest one to draw. Yes, Gabriel. We've got 3 minutes until you guys are officially eating into my lunch. So can I start drawing the wide belt? Okay. There might be enough room here. I can make it work. All right. Four. All right. Jump, jump, jump. Foil connection. Jump, jump. Foil connection. Jump. Foil connection. Tie all that together. Dot. Dot, 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 N1, N2, connection, jump. Let's see, 1, 2, 3, that's too big. All right. A for primary, B for primary, C for primary, neutral for primary, A for secondary, B for secondary, C for secondary, VLP, VLS. So we have VLS divided by VLP is equal to ILP over ILS is equal to A over the root 3 when we're going from Y to delta. And then VLS over VLP is equal to ILP over ILS is equal to root 3 times A. I don't know why I drew that delta upside down. Let me fix that. Delta Y. And then complex power on the primary has to equal complex power. All right, so those are our three different three-phase transformer configurations. Yes, please. Oh, let's see. So just line current, so it should be ILP and IL. So just current flowing down the transmission. All right, see you guys on Wednesday for just a crap ton of calculus.